In this video I'm going to go over some basic blocks that we're going to be using in order to generate the models throughout the course. And these blocks are generally what I think is important that you should understand how they work. So I'm going to do a quick construction of an equation and try and use as many useful blocks as I can. So I'm going to go ahead and go over to Simulink here. And as you can see, I've just pulled up a bunch of the blocks that I've been talking about, or that I want to demonstrate how to use, so you guys are familiar with them once you start building your own models. So in order to demonstrate how to use these blocks, I'm going to go ahead and create the equation that you're going to be using in the glider model, which is the FTR, tractive effort equation, that you should have seen a couple times in Module 1. So in this equation we're going to be solving for the inertial force Fi with FTR as an input, and this is one of the imports that we're going to use, so I'm going to call this FTR. And then in order to generate this equation, I'm going to need this sum block here, and it only has two inputs, so in order to change that, you want to double click on it, and you can change the number of inputs it has. So I want 1 plus for the FTR and then 3 minuses for the rest of the resisting forces. You can go ahead and resize this to make it a little prettier and connect FTR to the positive port. Right now I'm just going to use constant blocks to represent the rest of the resisting forces, but these are not constants. They should be equations that are calculated. So I'm going to connect this one here. I'll call this FRR. And then we need one for the aerodynamic force, drag force, so we'll call this F arrow. And then we're going to use this one, we'll call this F grade. Once again, these forces, I'm just using constant blocks to make it easier to understand, but this is not how it's actually going to be represented inside of the glider model. So once I have this equation set up, I have Fi at this port here now, given that all these values are correct. So I now need to find the acceleration. In order to do so, I need a gain block in order to divide by the inertial mass. So I'm going to go ahead and pull one of those up. It should be under here. Okay. So I have this gain block, and I'm going to say that this is going to be 1 divided by the inertial mass. Again, this inertial mass is going to be defined in the MATLAB workspace, so I can just pull up, use the right constant name, and that should give me the correct value. So here now we have the acceleration, and in order to get to the vehicle velocity, which is what we need to operate the model, we need to use the integrator block. So we can integrate once with respect to time. This integrator block always defaults integrating with respect to time. So this here we have acceleration, and now on the other side of it we have the vehicle velocity, which is what we've been looking for. We can actually duplicate this integrator block once more, so we can have position. So this signal here is going to be position, and we can just put that to an output. Actually, I'm just going to put the position to a terminator block, since we're not actually going to be using it here in this example. And this terminator block just makes this signal go to 0. Okay, so here we have the vehicle velocity V, here we have the vehicle position, we're going to call it X. So some of these useful blocks that we're going to be talking about here, first I'm going to start up here. This is a bus, and what this allows you to do is put multiple signals on one wire. So say if I want both the velocity and the distance on one signal, I can put them both, I can bus them together and put them on one signal this way. So now what this is going to do is this bus has both these signals, V and X, on the one wire here. And you can see them displayed right here, V and X. And if I was to export this to MATLAB workspace using this output, the way they would be organized in the y-out vector, or the y-out matrix, would be V would be the first column, while X would be the second column. if I wanted to pull each individual signal off of this port, I would use this, which is a bus selector. So let me go ahead and throw this in here. I can connect it here, and what this allows me to do is pick a signal that I want. So say I only want it to be outporting vehicle velocity to that port, I can select velocity here, and now you see I only have one signal. So, and that signal now is only outputting velocity. Another way to export data that you don't necessarily need to run the model, such as losses and things like that, but you still want to keep track of these signals, is you can export them to the workspace using the toWorkspace block. And that's what I have right here. So for example, if I wanted to keep track of the distance, which I don't necessarily need to run the data, run the model, I can have that signal going out to a toWorkspace block. And what this does is it'll store it in some way specified right here in the MATLAB workspace. So if I wanted to work with it very simply, I can just have it save as an array and change the variable name to x. So what this is going to do now is it's going to store the values of x in an array on the MATLAB workspace. Another useful block that we're going to be using quite frequently is the saturation block here. This is very useful for limitations to implement inside of the model. For example, if our powertrain had a limitation of, say, 8,000 newtons, I could implement that here. So instead of having just a free-for-all on the tractive effort, I can now implement some limits here. So if I wanted an 8,000 newton limitation on the tractive force, I can do it like this. So if the FTR that's going into here, into the saturation block, is between 0 and 8,000, it's going to output that number here. However, if it falls below 0 or above 8,000, it's going to saturate at the lower or upper limits and output that respective value. Another useful block that we're going to be using throughout the course is the switch block. The switch block can be used as an if statement to check conditions, whether which certain signal should pass through. An example of a good way to use this would be if our vehicle is stopped, we should not have a rolling resistance. Because the rolling resistance is a constant number and is not dependent on anything, even if there is zero velocity, the rolling resistance is going to be outputting a number, and that's not accurate. So how we're going to take care of this is we're going to put the switch block over here at the FRR signal. And one thing we can say, so the middle port is the conditional statement, and if that conditional statement is true, it passes the top signal. If it's false, it passes the bottom signal. So we want to be testing if the vehicle velocity is 0. And as you can see, I do have it. The criterion for passing the first input is if I want to change it to check for 0. So I'm going to put this one here. So I'm going to be putting the vehicle velocity into the check for 0 conditional part of the switch. And if this statement is false, I want to be outputting 0. So I'll put this stop phase, change this to 0, hook this up here, and if not, I'm going to put this signal to pass. So when this vehicle velocity is 0, I'm going to be outputting 0 to the FRR, which is more accurate because there should be no rolling resistance when the velocity of the vehicle is 0. If we are moving, the vehicle has any velocity, it's going to be passing the calculated FRR value. The last blocks that I wanted to go through are the go to and from blocks. These are pretty good for trying to clean up your Simulink model to make sure you don't have wires cross and everything like that. When you have a lot of these wires crossing like I do here, it makes your Simulink model get a little messy and hard to follow. So for example, if I wanted to have the tractive effort that I have going into the system go somewhere, I can link it up here, and then say I wanted to be outputting that to the workspace. So I can throw that on this block. Let's create another port on my bus here. So now I have 3 inputs. And what I can do is put this from block into this last port. I can label this one, say I'm going to label this FTR. So this go to block means this signal is going in here, and I can make it come out wherever a from block is. So I can update my tags here. I check there's an FTR now. Apply that. So now, with no wires, I have the tractive effort going from here to this go to block into this from block. These are just a couple useful blocks that I think will come in handy when you're trying to generate your own models. You don't necessarily have to use all these, but I think these are very useful tools when you're generating a efficient model.